Right, so again, page 174 and 41. F of x equals x to the 2/3 on 0, 1, and the instructions say, if the mean value theorem cannot be applied, explain why or why not. Okay, so MVT, there's only two conditions. It has to be continuous on the closed interval and differentiable on the open interval. Right? Continuous on closed, differentiable on the open. That's the only thing I'm having to check on 41. So it doesn't even, I don't even have to apply it. Just, does it work? Yes or no? Continuous. Let's see. I'm really curious about the endpoints, but if I plug in 0, I get 0. If I plug in 1, I get 1. There's no denominator, so there's no asymptotes. There's no sharp points. There's nothing crazy going on, so I'm pretty sure it's continuous. There's no holes, no jumps. We're good with continuous. Differentiable, I'm not sure about that one, so let's take the derivative and see what happens. I think we did this one as an example yesterday, or something close to it. So f prime would be 2 over 3, and I'm going to put the cube root of x in the bottom. Okay, well with that x in the bottom, this thing is not differentiable at x equals 0. But be careful, does it need to be differentiable at x equals 0? No, because the open interval means don't worry about at 0. So yes, at 0 is a problem, but we're not getting to 0 in terms of differentiable. So we're okay just barely on that one. Once in a while, I'm not sure myself if I go check in the back of the book to make sure I'm saying all that correct. I'm getting nervous, hoping I'm correct. 41 on page 174. Oh, I'm sorry, I only read the bottom part of the directions. The top part of the directions say, determine if it can be applied, and then if it can be applied, find the values where it works, basically. So, yes, it can be applied. So, yes, MVT works. Now I need to actually do the problem and find where it works. Again, I don't even, my first thought with MVT is always calculus slope equals algebra slope. So I don't memorize formulas. I mean, I know formulas that go with those, but MVT is calculus slope equals algebra slope. Calculus slope we already found. 2 over 3 cube root of x. Algebra slope, that's good old y2 minus y1. So I need f of 1 and f of 0. 1 to the 2/3 would be 1. 0 to the 2/3 would be 0. It gave me an easy algebra slope problem here. So 1 minus 0 over 1 minus 0, that equals 1. So my algebra slope is 1. So now the problem is set up. Again, this is the problem with MVT. It's just there's so many pieces to it. You got to remember the setup, then you got to do the calculus slope, then you got to do the algebra slope, and then you set them equal to each other. So 2/3 equals, I'm going to move the cube root over the other side. And then if I cube both sides, I get x equals 8 over 27. is the x-coordinate. Again, I'm cheating to make sure, not cheating, I'm checking to make sure I got that right. And yeah, it says in the back of the book, it phrases it as f prime, the derivative at f at 8/27 is 1. So that was another really good question, because it was, did MVT work? Yes, barely, because of the closed versus open thing, and then we had to do all the normal MVT stuff for it. Yes.
So if you're not sure what a graph looks like from the equation, and so when it's different, like when you're trying to figure out if it's differentiable, you take the derivative and see where the derivative, like what the increase is.
Yes.
But then what do you do to see if it's continuous or do anything?
So continuous, so it's a good question. So like, because you don't know what that graph looks like without a calculator anyway. And so how do you test continuity or differentiability? And you're right, for differentiable, you just take a derivative and see if something like this shows up. But that's the same type problems that for continuity. Continuity problems are jumps, but really the only way you have a jump is either the step function or a piecewise defined function where it's defined separately and there might be a jump. Asymptotes, but that happens when there's an x in the bottom. What other continuity issues are there? Holes, but remember that happens when there's a factor in the top and the bottom. That makes a hole. So you know all the issues to look for continuity. And then it's the same issues you're looking for, take a derivative and then look for those same issues. So it's a good question because you don't really know on some of these what the graph looks like. You just have to think about, well, what issues could there be? And it's a pretty short list of things that would make a continuity problem.